So today we're going to be talking about something slightly different. I actually got a request to cover this in a little bit more depth. And so this is going to be more of like an earlier type of lecture that we had this quarter, looking at a methodological approach, specifically optimization. So I'll note that this is like a very sort of high level view of optimization. If you're interested in learning more about this, there are like entire classes taught on even subsets of optimization. But hopefully what we'll cover today will give sort of a basic sense of what an optimization is, how to solve some basic ones, and then some information about the types of things that you would kind of learn from a typical sort of optimization course. Okay. So what is an optimization? So this is a problem where you would try and find sort of the best available values to achieve a specific objective, most often over some kind of set of constraints. And so we'll dive into this terminology in a second. But it's actually pretty easy to tell if the thing that you're working on is an optimization. So how do I mitigate emissions at the lowest cost possible? If you want to maximize profits related to energy production, how can I drive an electric vehicle with the most electricity possible? How can I minimize downtime for Uber and Lyft drivers? So anytime you kind of hear these words, maximize, minimize, lowest, highest, that's an indication that you have some kind of optimization problem where you're trying to achieve an objective that has a sort of really high value or really low value. Okay. So the canonical form of an optimization, this is known as the sort of negative null form, where you're always going to try and minimize the objective function. So I mean, the two possible ones, right, are minimization and maximization, but you can always convert a maximization to a minimization and vice versa just by adding a negative to your objective function. But it's very sort of prototypical to have a minimization. So you would have your function either as a negative version of a maximization or just as a straight up minimization. That's with respect to the decision variables. So the whole point is you're trying to achieve some kind of value, and the way you achieve it is by adjusting the value of specific variables in the equations. And so the things that are getting sort of adjusted up and down are going to be your decision variables. And this is going to be oftentimes, but not always, subject to a set of constraints where essentially the things that you're modifying might have some kind of limitations sort of placed on them. And so we'll be able to see sort of more concrete examples of this. But oftentimes the kind of language of the problem is pretty straightforward to kind of transform it into these sets of equations. Yeah, and so this would be some example of this. If you wanted to do energy production in the cheapest way possible, you would want to minimize the total cost, which is equal to, for example, the energy production times the marginal cost. And the decision variable in this equation would be the energy production. This is what you're allowed to modify. Okay, so actually really quick. So if I just had this, this set of information, so ignore the thing down here. Can anyone tell me what value of energy production I would choose? So yeah, so yes, kind of. So so you can do it like that. What would happen if you took the first derivative of energy production? Or sorry, of total cost. Well, what would happen if you took the first derivative of total cost? What would the answer be? Think more conceptually here. Like what, I'm trying to minimize this. What value of this would you choose to make this as low as possible? Yeah, I would choose negative infinity, right? Because that would be the smallest value you could get for total cost. And so you can see that I can easily satisfy this in that way. And in fact, if you do the sort of first derivative, you're going to find that there is no, because with an unconstrained problem, in this case, you're allowed to pick any sort of value. So this is where you have some kind of requirements. Energy production times, well, actually, this isn't going to help with that, but okay, so probably what I would have is an additional one. Let me see here. I would probably have an additional constraint where energy production has to be greater than or equal to some kind of demand, right? So that's the thing. So if I have some kind of constraint like this is going to prevent me from having this be equal to 0. It has to meet some demand. That's how you get this to be some kind of positive value. So more properly, I guess this would be like the sum across all technologies for each technology has to be greater than or equal to demand. And then you can have, like if you have some kind of cap on carbon, you could represent it in this way, where you have some energy production times carbon emissions, and that has to be less than some carbon limit. So you can see how we can layer in constraints to kind of reflect real world conditions. And then when you minimize this, you're gonna end up with some kind of real value this time, because you're not allowed to have negative infinity for energy production thanks to this constraint here. Yeah. Yes, I am recording, but thank you for the reminder. Yes. Okay. Okay. So there's a whole bunch of different like ways we think about optimization categories, and one of them is across its constraints. So the easiest is kind of unconstrained optimization. That means that you are just solving for some kind of objective function. You can have inequality constraint optimization, where your constraints have to be equal to some value. And again, in the sort of negative null form, everything gets set equal to 0, so you have to move everything to one side of the equation. In an inequality constraint optimization, you might have the less than or equal to, or greater than or equal to, but that's the same when you just kind of flip them on each side. And then a general constraint optimization, which may have both an equality and an inequality constraint. Okay. Another sort of important property, another important property of optimizations is known as convexity. So a convex function is kind of this, a sort of, you can think of this as like a bowl shape type of thing. And so we're just going to talk strictly about definitions for a second. If you have x and then you have some function of x, and there's a question of whether or not that function of x is convex. And the way this is determined is that if you draw a line from any point on the function to any other point on the function, it should be, if it is convex, it will always be above all other values of that function in that straight line. But if it crosses the line, as you can see here, if I pick a point over here and I pick a point on this side over here, then that will, actually let me draw it on here so folks online can see. So if I pick a point right here and I pick a point over here, you can see that that line is not always above the function. It crosses through parts of the function. And so that is considered a non-convex function. Similarly, there's a similar concept here known as a convex set. So if the region on the right-hand side of the graph, on the right graph, is kind of, if the set is defined as the region, then that set is convex in kind of the same way. So if I draw 2 points and there's anything hollow as I go from one point to another within that line segment, then it is not a convex set. And this is an important property for optimizations for a couple of reasons. So one of the things that an optimization does is it tries to look for these minimum values, right? And so one of the ways we can think about doing this, so this is, as was being mentioned earlier, like if I were to take the first derivative of my function at a specific location, what you can see is that in this case, you have 2 local minimum. And the way that some of the optimizations work is they're going to kind of start at some point and they're going to head down some kind of gradient until you get to a place where you can check and you can see, okay, I'm at a local minimum, or I'm at a minimum because the first derivative value is equal to 0. And in this case, maybe my algorithm would stop here. Okay, and but we can also see that that wouldn't be the right answer, right? Because there's actually another minimum. And so this point here is known as a local minimum, and then this point here would be the global minimum, which is lower. And when you have a non-convex function, you are not always guaranteed that the minimum that you're finding is a global minimum. And so non-convex problems are a lot harder to solve than convex problems. Okay, any questions about that? The other classification, yes. Yep.
So suppose our constraint kind of limits us only to the first part of this graph. Then the local minimum will be our global minimum.
Yeah, so if you have some constraints that only let you take values, let's say in this region, then yeah, that would be the best value in this particular example, but it's still more difficult because that function is still not considered a convex function. And so like it's kind of easy to visualize in this particular case, right? But you can't always kind of see it and know that the constraint that you're making just happens to kind of sandwich your like a particular minimum. So yeah, that can be really difficult. There are examples where like you could, well, okay, this is kind of a contrived example, but it might look something like this within your search space, right? And you could still you can end up here if you're searching in either direction, because you might skip over the gap if your step is like really large as you go down like a gradient. Yeah. Okay, so the last bit of thing that I'll sort of talk about in terms of classification is sort of across these different sets of ways that the functions the functions are kind of defined and the way the variables are. And again, like actually, you know, any sort of individual one of these boxes, you could probably take an entire class on. There's a lot going on in terms of like algorithms to solve particular types of problems and sort of different approaches even within each one of these classes. And so yeah, this is like a very sort of broad, important field. A lot of stuff actually still remains unsolved here. So let me just walk through the kind of different types of optimizations that you could encounter. So on the function side, this is what we were just talking about, where you could have a sort of purely linear function. So there's an entire class of these, a lot of like, a lot of the work that I do is kind of in this domain. So when we think about one of the things that I do is thinking about how power plants turn on and off to meet electricity loads. This is a type of a well-known type of linear problem. You can have nonlinear, these two here. One version would be convex. Okay, and so the most common for something like this would be like a function with like a quadratic term, which we know is convex. And then you just have a generalized sort of nonlinear function. And then in terms of the decision variables, very commonly you will have continuous variables. So these are variables that can go from, let's say, negative infinity to positive infinity, or negative infinity to 0, or 0 to positive infinity. These are all considered sort of continuous variables. Integer variables are where you have variables that take on discrete integer values. So there are, okay, and then mixed is where you have both. both continuous and integer. And so, I was just talking about these, so these models that simulate operation of power plants. They're called economic dispatch models. It's also common to have them as sort of mixed integer problems. And so one example of this would be if you're modeling power plants turning on and off, you have like a 0 for off and a 1 for an on, right? That wouldn't be able to be defined in this continuous way. And so now you have these binary variables, which are just a subset of integer variables. So complexity increases as you go from top to bottom and from left to right. Yeah. Oh, no, okay. Just no questions then. Yes. So if you have things turning on and off, where you have zeros and ones, like a binary type of thing, that would be integer. So the example before is like simulating power plants without this this startup shut off value. So basically, if you remember, there's this idea where you want to turn on power plants to meet electricity demand, and the order in which you do it is based off of their like fuel cost. So that's like a dispatch. And so you can imagine I can do something like this. I want to minimize generation costs. So let's say X generation is how much it's being used for each generator times some constant for generation cost for each generator. And then I would have, this is kind of like the thing we were seeing before. So such that X, if I sum up everything in X gen, that has to be, well, let's write it in negative null form. So minus demand has to be greater than or equal to 0, or equal to 0, depending on how you want to do it. So this would be an example right here. This example, it would be a linear problem. Yeah.
When you get like some raw data, is it pretty straightforward to determine like what sort of programming you have to apply? Like, is it often very clear whether it's linear or convex or general?
Well, the data shouldn't have anything to do with the formulation of the problem. The data is like how you would fill out values of like parameters. So something like if I have data to fill out this demand value and these generation costs. But yeah, but the problem itself, the formulation of the problem is strictly dictated by what you're trying to do. Yeah. So this isn't like a type of like data analysis type of thing. This is like a modeling type of thing. Although I will say, if you've ever done regression before, a regression is just a special type of optimization, right? Because in a regression, like if you're doing like a linear regression, what are you doing? You are minimizing the sum of the squared error term, right? So I said minimizing, so you should have alarm bells going off. Hey, that means that's an optimization. Okay. So let's do an example. All right, you run a small milk and cookies operation. Cookie costs 25 cents to make, and you purchase milk from a wholesale distributor for 10 cents. you hire a marketing team and you've determined that the quantity of cookies Q1 are in demand as a function of the cookie's price P1. And that relationship is defined as Q1 is equal to 0.5 minus P1. You've also determined that the quantity of milk are in demand as a function of the milk's price. Okay, so quantity 2 is equal to 1 minus P2. So what prices do you set to the milk and cookies to maximize profits? Okay. So who wants to help me walk through this problem? Okay, so what are the components of an optimization? So one is your objective function. So what is our objective here? What are we trying to do? Yeah, exactly. So right here, we are trying to maximize these profits. So maximize, let's have profits be defined like so. So what would my profits be equal to? Okay, so Q1 times the number of, wait, oh, sorry, yes. Yep. Price. Okay, so P1 times Q1. Okay, that's how much money I'm making. Minus what?
I mean, how much the cost of production.
Yeah, time. Okay, so let me do it like this. So let's do Q1 times whoa, what did I do? Sorry, one sec. Q1 times P1 minus 0.25. Okay, so that's for cookies, and then we'll dot for milk. Yeah, so that's right. So it'd be Q2 times P2 minus 0.1. Yeah, so Q1 is the number of cookies and Q2 is the number of milk. Yeah. Okay. So then, what do we do from here? Yeah, so actually, do we have any constraints? No. So actually, all you need to do is plug in your Q1 and Q2. Okay. So that's what we're doing on this next slide. Okay. So basically, I can plug in the value of Q1 into here, and then I plug in the value of Q2 into here. And so actually okay, ignore the next 3 lines. We'll just look at this again. So what, as the seller of cookies and milk, what am I allowed to change? Really? I can, the price, yes. Yeah, I can't control how much cookies and milk that people are buying, but I can control the price. So the prices are going to be our decision variables. Okay. So I am just going to substitute in the Q1 equation and the Q2 equation, which was 0.5 minus P1 and 1 minus P2. And then I go ahead and solve for this. I'm going to minimize the negative profit. So all the negatives, basically this whole equation gets multiplied by -1, and then I minimize this, and then usually the the way that you write it is with respect to your decision variables P1 and P2. Okay, so now I have this objective function here, which I'm minimizing. And so what would I do at this point? Did you have a question? Yeah. Yeah, so this should be it. It looks like this. So you like, oh, yeah, I don't know why this keeps doing this. You say minimize, and then the thing that you want to minimize, and then what that equation is. Yeah, exactly. I think it's a little confusing the way it looks here, because it looks like min minus. Yeah. It's when you see real people write it out, not in like class notes. Sorry, you'll see that like it's a little bit separated. So yeah, but if you see min or max, it just means minimize or maximize. Yeah. Okay. Yes. We're going to look at an example with constraints in a second. Yeah. Okay. So what do you think? How do we do this? I'm asking you because you were pointing this out earlier. Yeah, you do the first derivative, right? So this is your objective function. It makes some kind of shape, okay? And then the minimum, the minimum is where that the first derivative of that shape of the objective function is equal to 0, right? So okay, if we solve this by hand, you would do the partial derivative with respect to each of the prices. So if I do the first derivative with respect to P1 and the first derivative with respect to P2, you end up solving for this, and we want to set it equal to 0, which indicates that you are at the you are either at a minimum or a maximum. Okay, so in this case, I have 2p1 minus 0.75 equals 0 and 2p2 minus 1.1 equals 0. I can just solve for my p1 and p2. 0.375 and 0.55 are my values for p1 and p2. Okay, so then going back to high school algebra, I guess, how do we know that this is a minimum and not a maximum? Second derivative. So the second derivative has to be what? Yes. Okay, slightly more complicated. So you do the second derivative. So then you have dp1, 2, and then you do it with respect to each of the variables. So it's going to look like this. You have a 4 by 4. So 2p1 minus 0.75, if I do the derivative of this equation with respect to p1, that's just 2, right? If I take the derivative of this with respect to p2, that's just 0, because there's no p2 here. If I take the first derivative with respect to p1 here, this is just 0, and then with respect to p2, it's just 2. So you have this value. So you want to make sure that the eigenvalues are greater than 0, so you take the determinant of your second derivative equation, and you solve for your lambda. And this is greater than 0, so it's positive definite. So the solution's at a local minimum. So yeah, so folks in this class are going to be coming from sort of different backgrounds. And so I don't know if everyone kind of remembers how to do this, but the idea isn't to be able to solve this by hand, okay? It's more the concept of how this class of problems would get solved, right? So you would do the first and second derivatives, right? And nowadays the computer will do it for you. So you don't really need to worry about this, but this is kind of the machinery behind how some of the simpler types of optimizations would get solved. You would essentially do this. Yes. No. Okay, okay. So this is what you're trying to do, okay? But so I'm trying to do this minimization, and it could be a maximization as well. Yeah. But the way in which you solve it is through doing this type of thing. And so you were trying to do a minimization, you solve for this to get these values, but you don't actually know if you've achieved the minimization. That's the point. So that's why you have to do the second derivative to show that that this is what you're trying to achieve. And if this were negative, then you actually have to go back and say, actually, this is not right because we got to a value that we got to a value that we're not trying to achieve. Yeah. Okay, so there's a bunch of different ways we can solve this. So I'm just gonna show some quick examples of this so that in practice, folks can see. All right, give me one moment. I'm gonna pull up. So in Excel, wait, oh, other side. Okay, so so this is actually pretty straightforward to set up. I have my, okay, let me make this way bigger. Okay, so I have P1, P2, and profit. These are the three things in our model. And in the profit, this is defined as my objective function, right? So B1, so B1, which is P1. So B1 squared minus 0.75 times B1 plus my B2, which is P2 squared minus 1.1. So this is exactly the same. And so let's guess what this is. Let's say this is 3 and 1. Okay, so the way I would solve this, there is something called a solver. Yes. Hard to see from over here. Okay. Oops. Okay, so when you click that, there should be a little box that pops up like this. Yeah, one sec. Why is it not? It's not able to go past here for some reason. Okay. So in the data tab, there is on the far right side something called solver. It's not a default thing in Excel. A lot of times you have to have it as an add-on, but it's not something you have to like download or anything. It's built into Excel. They just don't have that option. So I would Google add Excel solver and it'll walk you through it. It's pretty easy. I just don't want to bumble around from memory right now. Okay, so set objective. So I just go to my objective function, which is B3, and click there. And I'm allowed, I want to minimize it. You can change it to the negative of that and say maximize if you want. And then you are going to change variable cells, these guys, these two. So you just select these guys, so B1 and B2. You can add constraints, but in this particular example, we won't be having any constraints. So I'm going to go ahead and solve this. If it will work, maybe. Okay, great. And so I end up with a value of 0.375 and 0.55, which is what we had solved for originally. You will notice that there's some kind of like rounding error, and this has to do with the way the particular algorithm that is being used in Excel is solving this. The way that we solved it analytically lets us get at exactly the right answer, but this is a more sort of generalized solver that may have some slight error because of it makes a decision to kind of say, okay, we're close enough, so I'm gonna stop. And again, if you want to learn sort of more particulars about how the solver is actually doing this, you know, there are sort of other classes that will sort of get more into those details. And I should say that you should be careful when doing this because actually sometimes if you don't know exactly what's going on, it might be giving you the wrong answer. So we're actually going to show an example later of kind of how to break this solver. Yeah, sure. Yep. Oh, okay, sorry. The solver is going to pop up with a box after that says like it's converged to a solution. And then you can choose to keep your solver solution. So I'm just gonna, don't know why my mouse doesn't work over there. Okay. Yeah, here we go. Yeah, sorry, it's really small, but it's right here. Yep. I will post these files on Canvas, so you guys will be able to see them. So another way to do it is with R. So ignore, oh, hang on, here we go. Yeah, I'm just, for those who are familiar with R, you can do it this way. Ignore lines 9 to 23. And let me, I'm gonna blow this up a little bit. There is a function called optim, which will solve this. And if I run this here, we will see that it returns your values that we're looking for our prices. So 0.375 and 0.55, same type of thing. Yeah, and there is another software called GAMS, which is designed specifically for optimization. And so I'll just note that that is a sort of common type of tool to do sort of larger scale optimizations. These, like Excel and R, will do simple stuff, but if you're really kind of getting into that sort of modeling territory, GAMS is the sort of software that is built to tackle, you know, complex optimization problems. And one of the nice things that I like about GAMS is that the translation from a mathematical formulation into the software is actually quite straightforward. So you can see here the way it's written out is basically kind of exactly as we do in the problem. So this is actually, sorry, referring to the next example. So let me jump back to here and we'll come back to solving these internally. Okay. So we're going to make our example a little bit more complex. So the local cookie mafia has demanded that you keep the prices of your cookies below 50 cents per cookie to ensure fair competition among other cookie businesses. Also, the Milk and Cookies Business Board has come to a decision that the combined of both items has to be equal to 70 cents. What prices do you set to the milk and cookies to maximize profits? Okay, so this is exactly the same problem as before, but now we are faced with some constraints, explicit constraints on the price. Okay, so in this example, okay, how would I do this? So can someone help me out with the formulation of the first constraint? Well, okay, hang on, we'll see. Yeah. So P1, yep. Yep, exactly. And I'm gonna write it like this, less than or equal to 0. So you could just plus and have it move to the other side. This is just negative null form. Yep. P1 plus P2, and I'm just gonna move it to this side, is equal to 0. Okay, so in this case, we have both a inequality constraint and an equality constraint. Great. Sorry, 1 second. Jump back over here. Okay. So if I write this out, that's exactly right. Now I have my same objective function, but now it's going to be a constraint optimization instead of an unconstrained optimization. I have these two constraints where, as we were saying, P1 is less than or equal to 0.5, and the sum of these two is equal to 0.7. Yes?
I don't know if this is, but I think the wording is that it has to be less than 50 cents, and so would that change it?
No, it does. But okay, that's like a very, oh, yes. Yeah, okay. Yeah, this is a tricky nuance with optimization. So, okay, what I'll say is that there's something called a binding constraint versus a non-binding constraint. So binding constraint is where this rubs right against the sort of value here, right? Because P1 is kind of free to be anything below 0.5, but right at 0.5, we call that constraint binding. So typically, you always include the equal to, because like mathematically, it could just be like just so slightly under, right? And so for sort of mathematical purposes, this type of problem is like way easier to solve than a strict inequality. Yeah, and so yeah, and in fact, like in practice, you almost never ever see like a strict inequality, because setting the inequality is almost mathematically equivalent and like way easier to solve. Yeah. But yes, good catch. Okay, so I'll just, so one of the ways this can be solved, so this is really common in like econ and like equilibrium types of functions and that sort of thing, as a sort of practical application of this. So you have something known as a Lagrange function and KKT conditions. So this combines the function being optimized with the functions describing the constraints. So you can think of it in a way where I'm kind of orienting the optimization so that I can basically shove my constraints into my objective function. So there are a bunch of like conditions that you have to fulfill to make sure that it's optimal. Actually, really quickly, what kind of optimization problem would this be? Yeah, but no, among the like classifications that I talked about, like so are the variables continuous, integer, or mixed? And then are the functions here linear or nonlinear? They're not linear, that's right? Because I have these squared terms. So definitely not linear, might still be convex. And then how about the variables? Are these continuous, integer, or mixed? Yes, linear, continuous, or not linear, continuous. Linear is the formulation. For the variables, right, these can take on basically any value. They're not set to like discrete values, so it's not integer. Okay. So these are the KKT conditions and the Lagrangian. Basically what this is, again, we don't need to get super in depth into kind of the details here. This is like one of the algorithms that someone really clever has sort of devised to solve this maximization, okay? And so when you take a class on this, you learn a lot more about the sort of background and why this works and that sort of thing, but I'm kind of just showing you here. So you create this Lagrangian, and basically this is your objective function. And then as I was mentioning, we basically push the constraints into that function. So you have for your equality constraints, you basically have lambda times your equality constraint plus, I'm totally blanking. What is this symbol? Sorry, what was that? Mu. I think, yeah, I think that's right. So mu times your inequality constraints, and we'll show kind of this works. And then you have these sort of 4 KKT conditions. It's called stationarity, primal feasibility, complementary slackness, and dual feasibility. And this is the first derivative of your Lagrangian with respect to x, with respect to lambda, and respect to mu. Okay, this looks a little bit complicated, but we'll show how we can apply this to this problem. Okay, so again, objective function here, the top, and our 2 constraints. My inequality looks like this in negative null form, and my equality looks like this in negative null form. And so the Lagrangian is simply your objective function plus lambda times your equality constraint plus mu times your inequality constraint. It looks like this. Lambda is just a sort of, it is, so it actually represents some kind of like marginal value, but it's essentially just this this variable that's allowing you to do this combination of your constraints into your Lagrangian function. If you follow these rules, it'll let you essentially solve for your x's. So it's kind of like this arbitrary variable that lets you do this solution method. Okay, so if you have this, then you have a bunch of, you can then have your KKT conditions, which look like this. Okay, so these are your first ones. So this is the derivative of lambda with respect to P1, with respect to P2, with respect, or sorry, your Lagrangian with respect to P1 and P2, with respect to lambda, and with respect to mu, right? Okay, and so then you have your last KKT conditions here. And essentially what you've got going on is a whole bunch of equations and a whole bunch of unknowns, and then you can go about and sort of solve them. And so let me see. Okay, so if I were to go about doing this, the key thing in solving this is that you have something known as binding and non-binding, which is what I was explaining in your inequality term. Right here, you have this kind of slack variable that lets you decide whether P1 is the thing that sets this equal to 0 or if it's something else. Okay, so if P1 is 0.5 and that makes this equal to 0, then that's your binding constraint. And if mu is equal to 0 and P1 is allowed to be something else, that's a non-binding. So let me do this. So basically in the binding, it's a little bit easier, right? So let's just say in the binding, P1 is equal to 0.5. So we'll have 0.5 here. And then I can then solve for P2, right? Because I know what P1 is here. So then P2 would just be 0.2. Pretty straightforward. And now that I know P2, I can solve for lambda here. So 2 times 0.2 minus 1.1 plus lambda equals 0. And lambda would be equal to 0.7. Okay. And then I know my P1 and I also know my lambda. So I can solve for this equation here. And this would be equal to negative 0.95. That actually violates this guy here at the bottom, but this is only active in your non-binding constraint. And so I can now take all of my values that are defined here and then solve for my profit. And what I'm going to do is I'm going to compare that against solving it in the non-binding way, where I'm going to say instead of, okay, so instead of my P1 equaling 0, I'm going to have my mu equals 0. So this is going to be 0. And so this is now going to be a little bit trickier. But the way that you can solve this, so I have some equation 2p1 minus 0.75 plus lambda, and now the mu is gone. So that's equal to 0. So if I get rid of this guy, so I now have 1, 2, 3 equations with P1, P2, and lambda. So 3 equations, 3 unknowns. So you can do some basic algebraic manipulation. So I also know 2p2 minus 1.1 plus lambda equals 0. And then P1, let's say, is equal to 0.7 minus P2. So that's just reconfiguring this guy. I can take P1 and insert that into here. So then I would have 1.4 minus 2p2 minus 0.75 plus lambda equals 0. I now have 2 equations with 2 unknowns. So the other equation is 2p2 minus 1.1 plus lambda equals 0. You can add these together. My p2s will cancel out. So that will be something like 2 lambda is minus 0.45 equals 0. And then I can solve for my lambda, which is going to be 0.225. And I can go back, plug these in, solve for my P1 and P2, and I will end up getting 0.4375 and 0.2625. Now I can take these prices, plug them into the original profit equation. In this case, this would be like negative 0.1928. So this value you're going to find is more negative than this value. And so our non-binding, the non-binding one is the one that has lower profit and therefore is the sort of correct answer. Yeah, because we put a -1 in front of the profit. Wait. Yes, that's right. It's more negative. And so so this would be, I didn't actually take the time to solve the profit for this, but it's going to be less negative than 0.1928. So let's say it's -0.1, for example. So then the positive profit would be higher, right? Because 0.19 is greater than 0.1. So if this were, yeah, it's more negative. Yeah, so the positive version of that. Yeah. Yep. Okay. So this is like an example that's like solvable by hand. And again, this is kind of just to demonstrate one of the types of machinery behind how you could go about solving a simple sort of optimization like this, right? And you can see, we came up with this mathematical formulation pretty easily based off of, these sort of real world descriptions of constraints that are happening. And you can imagine how there's lots of analogs for this for all sorts of different problems in the real world. People aren't going about solving this by hand, but this is, again, just to give a sense of how some of these things had come about. Okay, and then I can show some examples of how you might do this in, for Excel, for example. Let me zoom in. Okay, so let's, let me change this. So you can actually see that the solution that it solved for is the same as what we had. I'm just going to change these. Okay. So the profit function is exactly the same as before, right here, but now we have two constraints. So constraint 1 and constraint 2. So this is just B1 minus 0.5 and B1 plus B2 minus 0.7. They're in the negative null form. And when I click the solve guy over here, and I need to bring this box over. So it's exactly the same as before, except now I have these constraints. So B5, you basically click here, you add, and then you can choose. Okay, I'll delete this one and I'll add it again. Oh, sorry, the box is always on the other screen. So I'm going to say this is less than or equal to 0, right? And you can select all the sort of different types of constraints. Is mainly going to be these 3 up here. And I'm just going to hit OK. That's going to open the other box again. Okay, and so you can play around with the settings here to make sure you're adjusted to your system, and you hit solve. And okay, great. So our profit that we had calculated, oops. I'm just gonna click OK to keep these answers. Okay, so negative 0.1928, which is what we had solved for by hand, and then 0.4375 and 0.2625 is what we had solved for by hand as well. So Excel is able to solve this type of problem. You can do that in R as well. This time I'm going to use a slightly different solver that allows you to use constraints, and you can write your objective function and your constraints explicitly as these functions. And I will kind of use the solver here, and I'll just show you. Oops. If I run this code, it will give me in this it'll actually tell you the Lagrangian values, so 2.25, which is what we had before, and then our parameter values will be 0.2625 and 0.4375. Those are going to be your prices, same as before. Yeah, and so lots of different ways you can solve this, lots of different tools you can use, and GAMS as well, as I was mentioning, is able to do this. And I will, yeah, I'll make sure to upload those files on Canvas so folks can reference them. So the ways that I had just sort of gone through when we do it by hand, those are what are known as sort of analytical solutions. And so analytical solutions are always going to give you the exact answer. And we showed some examples of how essentially we're kind of solving these by hands, but basically you're taking these equations and explicitly solving the values that would solve your optimization problem. If optimizations could be solved in this way, everyone would do it like that, because because your solution is always going to be the perfect solution. But unfortunately, you can imagine that like the equations start to get really, really complex, and you aren't always able to do these analytical solutions. And so in fact, it's a lot easier in many ways to do these numerical methods. And so these are kind of what are known as iterative methods, essentially where you're kind of guessing and checking. So instead of like solving for P1 and P2, I'm going to say, I'm going to make an educated price about what I should set for P1 and what I should set for P2. I'm going to look at my objective value, and then I'm going to choose a different price and see if I can lower that objective value. But it's done in a really sort of smart way. So it'll look at things like gradients. So you'll always try and decrease the value of your objective function if you're doing some kind of minimization. And there are lots and lots of different numerical methods for linear, for unconstrained, for constrained. And these are types of algorithms that you would learn in a optimization course. And again, like these are all pretty specific for different types of problems. And so depending on the context of your problem, you could learn about sort of very specific analytical and numeric methods for solving them. So when you use an optimization solver, it's oftentimes a good idea to have some knowledge about, it's a good idea to have some knowledge about the type of solver that's being used. Because in fact, if you're applying it in sort of the wrong way, or if you're applying it in such a way that may sort of counterintuitively not work with the sort of algorithm that it's using, you could get into trouble. Because one, you could get into instances where the solver can't actually solve, which is not great because you're not getting a solution for your problem. But worse, you could actually get a solver that solves and it gives you the wrong answer and you wouldn't even know. So I can show you a sort of quick example of this. So Excel uses what's known as a generalized reduced gradient solver. This is a numerical method, which is one of the reasons why it's not getting the exact answer that we had when we did the analytical solution. And a solver can fail for many reasons. It can get stuck in a local minimum. There can be no gradient information. And then you can have convergence at really steep slope areas. So let me show you what I mean here. All right. Okay, so this is an example of an optimization. And the problem is, okay, you've got some kind of cylinder here. And I want to maximize the surface area of the cylindrical pill. And you have some design objectives and some constraints, and essentially what you're allowed to modify. So you want the radius of this to be positive and you want the height to be positive. And you are trying to make the surface area of this as small as possible. So here, there is a specific constraint that basically says the volume of this can't change. So given a set volume for your cylinder, how can you make the surface area of it as small as possible? And you're allowed to change your design variables, so your decision variables. So I can change the radius and I can change the height, but I'm not allowed to change my volume. Okay. So let me just go, let's say we'll start at 2 and 3. So here, so the volume is too big, the area is also too big. So these are not like good starting values. You're already violating your constraints, but let's throw it in the solver and see what happens. So solver here. Okay, so my objective is to minimize my surface area here. It's the same as this number. I'm allowed to change my radius and my height, and then subject to constraint. So C7. Yeah, so the volume has to be equal to 10. This is what this is doing. And then these guys just are indicating that it has to be positive. So I'm just gonna go ahead and hit OK and solve this. Great, okay. So we can see that in this case, I have a volume of 10. So that checks out with that constraint. And then I have a surface area of 26. So that looks good. And I'm going to say, keep my solver solution. So the way the numerical solvers work is it takes your starting guess and then it starts to move in the correct direction from your starting guess. So based off my starting guess, we arrived at this optimal solution, looks pretty good. But what happens if we give it a really bad sort of starting suggestion? So let me do this. I think it's something like this. Okay, so let me try this again. I don't remember exactly what I needed to do to break this, but hopefully this works. Nope, okay, it's still getting to the right guy. Okay, let's make this more extreme. Uh, 0.001 and 1000. No, you can start at 0. I made it really small in this case. Yeah, you can give it nonsense starting values and it would still solve. Well, not necessarily. Like the starting values, like if you have a decent algorithm, it should be able to figure it out. Okay, cool. So I hit solve, and this is what it gave me. You'll remember that this was at what, like 25 before in the other one, but this is telling me that I didn't get any error warnings or anything like that. It just gave me the solution. Yeah, and so this solution is a lot larger and it's incorrect, right? And so that's the danger of kind of blindly doing this, is that you could have a incorrect answer. So let me give like a sort of qualitative reason for why this could be happening. So if you're solving some kind of function, maybe that looks like this, and you kind of start here, maybe qualitatively, like what a numerical solver might do is it may kind of look in all directions, right? And it could say, it says, if I take one step in this direction, I can see that my objective value is improving or not improving. And so I'm going to choose to go in this direction and keep doing this, right? But you can imagine, what if my function looks like this? What if my function looks like this? And I choose to start over here, and I go this way, and I go this way, and I say, oh, I don't see an appreciable improvement in my objective value as I take steps in a certain direction. And so I'm going to say we're good to go because it looks like I'm in the right place. And so you can get stuff like this happening. So that's just a kind of word of caution for doing these sorts of things. Yeah, one way is to try and use a bunch of different starting values to see if you arrive at the same solution.
And is there a problem with any kind of optimization?
Yeah, so kind of. It depends on the context of the type of solver and the type of problem. I guess the idea here is that like I'm introducing you guys to optimization without all the like deeper sort of background theory that you would learn from other courses. And so I just want to caution, like before you just start using the tools, is that there are some issues with getting solutions that might not be strictly correct. Okay. Back to lecture. Okay. Optimization, it's used everywhere. Okay. Any sort of sector you can think of is probably using some kind of optimization to some degree. And there are actually some unsolved problems in optimization that if someone were to solve in the future, you would probably become like a billionaire instantly because you'd be solving like logistics problems, for example. If you've ever heard of like the traveling salesman problem, there are these sort of simple formulations that are actually like computationally very, very, very difficult to solve. And it's very difficult to guarantee like the correct answer. And so, yeah, you can imagine that the application of these optimizations is sort of very, very widespread. Okay. Any questions about optimization? Okay, so I guess it is our sort of last class, so I wanted to wrap up a little bit, jumping back to sort of the higher level stuff that we're doing at the end about policy analysis and sort of the application of a lot of the modeling tools that we have done in the context of doing sort of policy analysis. So, okay, how do we apply critical thinking and analysis to other policies in either transportation or in energy sectors, right? So we've talked a lot about this sort of stuff. So economic analysis is really important in decision making, thinking about sort of when I do make a decision, why am I making that decision? A lot of that oftentimes comes down to sort of costs versus benefits, right? And so the type of monetary analysis that we're doing when we think about time discounting, levelized costs, all of that stuff actually plays a really important role in, for example, decide if an investor is deciding to invest in clean energy, or if a policy maker, right, is deciding to help push through a law that may be funding these things. The economic analysis is almost certainly playing a role in that decision-making process. Technological viability, thinking about how technologies work, what would they be competing against? Does the infrastructure already exist to support it? How long does it take to be adopted? Right, we can think about a lot of those, like diffusion, adoption curves, about learning rates that we talked about to help address some of this. Decision making, a lot of the risk analysis is really helpful in understanding sort of the options that you have in making a decision, and what sort of impacts that would be coming out of them. Uncertainty and sensitivity analysis. It's something that I think is really important. We don't see enough of in a lot of different types of analysis. You never really have kind of just one answer, right? Parameters will have lots of uncertainty, and you have to know how to kind of deal with that, how to display outputs where you have considered uncertainty in your parameters. Yeah, and so I think I'm just gonna leave it here. There's a couple examples of specific policies in the slides, but I'll let people kind of look over them. But we'll kind of close out here for our quarter, I guess. And I guess the next time we meet, I will be in the audience watching you guys present. So any questions about any of this stuff? Anything in the course? All right. Well, thank you, everyone. Let me stop recording. If I can, what happened to my Zoom? Okay.